Can we get the screen? Is it possible to get the screen share?
No.
She's not in the meeting. Oh, do you have slides? Oh, no, you
I
have slides
emailed
here.
slides to Myra.
Yep. Okay, perfect. Thank you. Sorry.
Because your system won't accept a Linux computer.
Okay, go ahead.
Okay, are you ready to go?
Yes.
Okay, so what you should have on the screen now is my title slide, which is the obligatory pretty picture of the telescope. So if you go to the first one, the Giant Magellan Telescope, or GMT, is a collaborative effort between universities and research organizations, and you can see here the different partners. Obviously, some of those are U.S. institutions, and some of them are non-U.S. institutions, including 2 in Australia, 1 in Korea, 1 in Brazil. University of Texas is one of the founding partners of the collaboration, and that's what I represent. Next slide. So I gather you've heard about the TMT and probably know something about the European ELT, which are large numbers of 1.4 meter mirrors. In the case of ELT, it's almost 1,000. In the case of TMT, it's almost 500. But unlike the other giant telescopes, the GMT is using only 7 mirrors, but each of the mirrors is extremely large. It's an 8.4 meter mirror. They're being made at the Mirror Lab in Arizona, which happens to be where I am right this moment. They're the largest mirrors that they can make in the Mirror Lab right now. So when you put 7 of these together, the total primary mirror is 24.5 meters, with the gaps that you end up with, and I'll show you a picture in a second. The effective aperture is 22 meters. It also has a unique 7-mirror secondary, and it is the secondary that will be responsible for the adaptive optics. These are adaptive secondaries, similar to what's on the MMT. And each one of the secondary mirrors is focused on one of the primary mirrors. So the first mirror was cast in July of 2005. It's completely polished. It's sitting in a warehouse outside of the airport in Tucson. Mirror 2 is essentially complete. I gather they're going to just do a little bit of polishing up, and that's it. And then 2 will probably go out to the warehouse, which is sitting right next to the LSST mirror, incidentally. Mirrors 3 through 5 have already been cast. They're in different stages of cleaning out. You've got to clean the front surface, the back surface, and then 3 should be going into polishing very soon. And we have the glass in hand for mirrors 6 and 7. So all the mirrors are either in process or the glass is funded at this point. Next slide. So this is I love this picture because it's the mirror sitting in isolation from everything else. You see the person standing next to him, give you a sense of scale. The middle mirror, the number 4 mirror, therefore, is the one with the hole in the middle of it, and all the external mirrors on the outside of the central mirror are of an appropriate figure for the telescope. Next slide. So this is the parameters for the telescope. The important thing is it's an aplanetic Gregorian, which means that it comes back to a focus and then goes, the secondaries are above that. And that gives you a very, very wide field of view. So the field of view of this telescope is 20 arc minutes in diameter, which is much larger than any of the other extremely large telescopes. If you can do AO correction, you get diffraction limited angular resolution of 0.01 arc seconds at 1 micron. And that should be of pretty good interest to people who are interested in small bodies, especially small bodies that have companions to them. The wavelength range is 0.32 to 25 microns, so it goes through the optical into the near infrared and into the mid infrared. Next slide. So this is a picture of the structure with the mirrors in their cells with the secondaries above them and the big C mounted here. Again, there's a person in the picture, so you have some sense of scale. At this point, we have 2 different firms that have been working on the design of the mount. The mount is everything except for the building or the mirrors. So everything in this picture that you see except for the mirrors is the mount. The final mount producer will be chosen in the next month or so. I'm not sure if there's any delay because of the shutdown of government, but most of the companies have a strong European component to them. So we will actually have gone to contract with the company that will be building the mount within the next month or two. Next slide, please. So the telescope is going to be sited in the southern hemisphere in Chile at the site of the Las Campanas Observatory. This is an artist impression of what it looks like with the telescope sitting up on the mountain. And I believe in this view, the Magellan telescopes, the twin 2.5-meter telescopes, would be behind and slightly to the left, but they're not showing up in this picture. The next picture shows the site as it was last month in December. So you can see we've made substantial progress in developing the site. There's also a lot of the support buildings at this point. They're further down the mountain. But you can see the area where the wall of the dome will go, and then the center part where the pier will go. The building that's up on the top is actually a construction building that will go away. The red and white towers in the background are test towers for air quality, for image quality and testing and stuff like that, and they'll stay up at all times, I think. So, I mean, this telescope is going to be a reality. It's quite under construction at this point. Next slide. So, the first light is, to some extent, a political designation because we're going to define it as the first science phase is 4 mirrors out of the 7, plus 1 or 2 instruments ready to be used without adaptive optics. So the concept here is that we will have three of the outside mirrors that are adjacent to one another and the central mirror so that you can actually develop the adaptive optics at the same time as you're doing the first of the science. And at the time that this will be in this mode, which is slated right now to be late 2024, it will be the largest telescope in the world at that point. Next slide. So this is a graphic that shows you what happens when you go to a large telescope in a good site with adaptive optics. The first panel, the A panel, is natural seeing of a field with 0.5 arcsecond resolution. And 0.5 arcsecond resolution is not particularly difficult for the Las Campanas site. That's very typical for that site. It's a very good site, even though it's not as high as some of the other sites. In panel B, the second panel from the left, that's an HST image of the same area with 0.2 arcsecond resolution, so obviously much cleaner looking. Panel C, which is the third panel, is simulated JWST, obviously that hasn't flown yet, and that's 0.07 arcsecond resolution. And then panel D is the simulated GMT with natural guide star AO, and in this case it's 0.02 arcsecond resolution. So you can see how you improve dramatically, and you get 10 times the angular resolution that you would get with the Hubble Space Telescope because you have such a large telescope and with excellent adaptive optics. Next slide. So this is a picture of the telescope showing where the various instruments can go. There are 3 different places where you can put an instrument. The green box on the bottom there is GCLEF, which is a high-resolution spectrometer, and it's a gravity invariant area because the idea here is that you're going to be doing high-precision radial velocity work, so you don't want it riding along with the telescope as the telescope rotates. The blue boxes on the right-hand side is the direct Gregorian feed, and it's where it will be like a Cassegrain focus on a typical telescope. It's where you can put a big instrument or 4 instruments and be able to trade one in for another one. Then the red optics in the left side is the folding port. So there's a folding port where it shows M3 subsystem, and you can fold into a series of instruments that rotate with the telescope. Next slide. So this is the first generation instruments. GCLEF, I mentioned, is an optical high-resolution, high-stability spectrograph. It will have resolving powers of 20,000 to 100,000. Can be used in natural seeing mode, in ground layer AO mode, and in natural guide star AO mode. GMAX is the second instrument that will come online, and that's a wide field optical multi-object spectrograph. Again, it's in the optical entirely, and goes from, oops, there's an extra zero in that. It goes from 1,500 to 4,000. Again, it's natural seeing or GLAO, and has a very large field of view if the fibers are just packed normally with to 43 arc minutes squared. But if you jump down to the bottom of this slide, there's an instrument called Manifest, which is a Starbug system being developed in Australia. It's the Facility Robotic Fiber System and can get to the whole 20 arc minutes of the telescope with fibers that can feed any of these instruments. The other two instruments are GMTIFs, which is a near-IR IFU spectrograph and imager with 1 to 2.5 microns and moderate resolution, and two different field sizes, and GMT NIRS, which is a near to mid-IR high-resolution spectrograph, which goes from 1.08, and the reason it doesn't get the whole of the J-band is the silicon band gap, all the way out to 5.4 microns. It's at R of 65,000 in JHK and R of 85,000 in L&M. So if you go to the next slide, I've highlighted two of the instruments, that's GMTIFs and GMT NIRS, and those are the two instruments I think would be of most interest to the people in the room there. We tend not to have a lot of objects together, so a multi-object spectrograph is generally not of terrible large interest for small bodies people. But GMTIFs is a small field of view, but very high angular resolution and moderate to, well, medium resolution infrared instrument. And that would be absolutely perfect for doing something like looking at binaries, looking at Kuiper belt objects. When you can have diffraction limited imaging of 0.02 or 0.01 arc seconds, you can do an awful lot with an instrument such as this, even with a small field of view. The other instrument, which is near and dear to my heart, that happens to be being built at the University of Texas and at CASI in Korea, is GMT NIRS, which is the near to mid-IR high-resolution spectrograph. You get all of JHK, L, and M at high spectral resolution in one shot. So this is going to be an incredible instrument for doing things like looking at comets to get the spectra of them, or looking at planets to get the spectra of them. This is a feed-on to an instrument called IGRINS, which is currently at Gemini. No, it's actually currently at the DCT, and it will be back at Gemini in the fall. So this is an instrument that really has a lot of advantages for people who like spectral resolution in the infrared. Next slide. The other things I think you probably care about is non-sidereal tracking. The decision was made to be able to track targets moving at non-sidereal rates up to 6 arc seconds per minute. That eliminates the really close things, but it allows us to be able to get image quality for seeing limited observations over small fields of view with no more degradation of the point spread function than 0.1 times the point spread function elongation. The telescope will be able to go down to 30 degrees elevation angle with a goal of 25 degrees, so you can't go all the way to the horizon, unfortunately, all the way up to 89 degrees, and of course it's an Albaz telescope, so going right to the zenith is not a normal option, but hope to get to 89.5 degrees. And for spectroscopic modes, they'll be able to nod accurately back and forth for sky cancellation between two specified positions and integrating at both ends, similar to what's done with something like NIRSpec. And I believe that's my last slide, so I'm happy to take questions.
Questions for Anita?
Do they have any issues with the N-band? N-band.
Do you have any instruments that cover the N-band in IR?
Not in the first light instruments. There is talk of second generation instruments, but those have not been selected at this point. The telescope can, of course, go out that far and go out to 25 microns, but nothing is in the first generation of instruments at this point.
Has there been any discussion of how much time solar system science might get.
Has there been any discussion of how much time solar system science will get?
It will be entirely dependent on proposals to the telescope allocation committees. There is no guarantee of time for any project in any field in astronomy. There is guarantee of time for the partners based on their share of the money that they've put in. And so it's then up to each partner. Well, there'll be a combination of partner tax and combined tax that will decide what science gets done.
All right.
So I have a question from Tim Lister, who asks, how hard is the 6 arc-second minute per limit on non-federal tracking? Any opportunity to increase?
Okay, so an online question: how hard a limit is was it 6 arc minutes per?
Sorry.
6 arc. Okay, yeah, 6 arc second per minute. Yeah. Okay. Anyway, how hard is that limit on tracking? And was there a follow-up part of that?
Is there any opportunity to increase that?
And is there any opportunity to increase that?
That is the design spec at this point. A lot will depend on what comes in the mount models and the decisions, but that was where they felt the sweet spot was between doing most of the science possible and not pushing the image quality down.
All right. And go ahead.
I have another question from Martin Elvis, who asks, will GMT be able to do target of opportunities? Will it be queue scheduled?
Another question, will GMT...
I got it, I heard it.
Oh,
Yeah,
okay.
yes, there will be queue scheduling. Whether it will be 100% queue scheduled or partially queue scheduled and partially classical scheduled is still very much up in the air. Some of us feel like it should be 100% queue scheduled, but we don't always rule. And target of opportunity will definitely be part of the consideration.
All right, any more questions, person online? All right, thank you very much, Anita.
All right, I'm going back to my other meeting. Bye.
Okay, thanks.